friends, welcome to the channel Physics by IITians. In this video lecture, we start another lecture series, that is Statistical Mechanics. This Statistical Mechanics lecture, you won't be only be able to solve the numerical problems, but you will be able to understand the physics behind the statistical mechanics. You will physically interpret the terms and you will understand why and how these terms are allowed here to explain the physics behind each and every aspect in the macroscopic or microscopic worlds, or what are the terms meaning and what are the things that we do in statistical mechanics to understand the fundamental laws of physics. Okay, so this video lecture will be very much crucial for you if you love to understand the physics besides the solving the numericals. So let's start the video. I will request you to I will suggest you to read these books and follow these books for understanding it deeper way. It is RAFE, Fundamentals and Statistical Thermal Physics, Mehran Kardar, Statistical Physics of Particles, Landau and Lifshitz, that is Statistical Physics, and R.K. Pathria, Statistical Mechanics. So our test series has also been launched, so please join our test series, and if you have already joined, our second full length test access will be available from 7 September. So you can choose any time you wish to join for the test, and you will also get the solution paper after 5 to 6 days so that every candidate can finish that. Okay, so let's start the video. Before starting the video, we understand some basic laws and their philosophy, means their physics, and we'll choose these laws from 1600, that discovered from 1600 to 1900. Suppose we are taking the Boyle's law, Charles law. What does it tell? It relates the pressure, volume and temperature of gases. Stefan Boltzmann law, it tells how much energy a hot object emits. Wiens displacement law, it tells the color of that hot object, because lambda into T is constant. So lambda is associated with that color of the body and T is associated with the temperature of the body. So the color of that hot object that emits. Dulong-Petit law, how much energy it takes to heat up a lump of stuff. Curie's law tells us that how a magnet loses its magnetism if you put it over a flame. Like if you suppose heat a magnet, okay, so after certain temperature it loses its magic. So this behavior will give you the Curie's law. But we all know that these laws are not fundamental. We have to find it something fundamental, or some laws that is giving you the fundamentals of the physics. So why do we need that? Suppose I am giving you a box, and this box is containing 10 to the power 23 particles. Now you know their mass, their charge and their interactions and so on. So what can you tell me about the stuffs inside the box? Okay, so possible answers. Okay, ma'am, you gave me the box. I can solve the Schrodinger equation for each of the particles, and then you can find out the wave function also, and then we can find out the properties, microscopic properties, means each and individual dynamics of the system, dynamics of the electrons, dynamics of the protons, dynamics of the neutrons, and you will find out. But friends, is it fruitful? Because 10 to the power 23 is a huge number. Okay, and it is not possible you to solve 10 to the power 23 equations individually, and then you have to calculate all the things. I mean, this is totally ridiculous. Okay, and my questions are actually that the box is wet or not, is it hot, what color is it, is the box in danger of exploding, what happens if we squeeze it, if we pull it, if we heat it up. So how can you begin to answer this kind of questions starting from the fundamental laws of physics? Suppose if the particles represent a gas molecule at temperatures at a normal temperature inside a closed container. So which of this figure will give you the configuration, or which of the configuration will comes first in your mind? This one or this one? Obviously this one. Okay, you don't think that this is the picture which you think that this is the correct picture for that gases inside that container. Because in the macroscopic world, suppose we take an example that you toss bricks of truck, and which kind of pile of bricks would you more likely to produce? Not this one. This one will be more likely to be produced because disorder is the more probable choice than the order in nature itself. So this is a highly unlikely configuration and this is highly likely configuration. And suppose now this was all in terms of the kinematics of that particles or gas molecules. So this is the kinematically or kinetically dominated field. So this one as the time goes on, the system will be more disordered and this kind of configuration you will going to see or you will going to observe. But if the field is gravitationally dominated field like the black holes, what will happen? At the earlier time it was scattered, but as the time goes on you will get this configuration totally different. So all this macroscopic behavior are actually decided by the microscopic fields, microscopic interactions, and the interactions between the particles, the interaction of that particular field with the particles. This will decide you to the macroscopic behavior. Some of the particles or some of the systems are going to behave something other than the uh, other system, and this all are dominated by that particular kind of interaction which is happening between these particles or at the microscopic scale. Okay, so the statistical mechanics is the art of turning the microscopic laws of physics into a description of nature on a macroscopic scale. So who is the artist here? That the artist which is going to give you the relation between the macroscopic world to the microscopic world, that artist name is the statistical mechanics. So it relates the microscopic world where the laws of nature are written to the familiar macroscopic world. And this will allow us to begin to address very basic questions about how matter behaves. So the statistical mechanics is a crucial tool for understanding the deeper laws of physics. High temperature superconductors to black holes, they are not yet understood at a fundamental levels, and we only have the information of the macroscopic properties. So our goal is to use these behaviors, that is macroscopic behaviors, to deconstruct the underlying mechanism at work. So some cautious statement that Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand, means he committed suicide. And Paul Ehrenfest, actually, he also carrying on the work and died similarly in 1933. Sorry. So he also committed suicide. So now it's your turn to study statistical mechanics, and so it will be wise to approach the subject cautiously. Okay. So thank you friends, thank you for listening and watching this video. So we shall discuss more about the experiments, about the physics, about the statistical mechanics. Do not forget to like, share, subscribe to the channel. Do not forget to join the test series. It will be helpful for you because the cost has been kept minimum for your benefits only. So all the best my friends. Thank you.